Now, another categories of this creep resistance steel is austenitic creep resistance steel. So, previous case you see there is the main composition is chromium only, but here in austenitic creep resistant steel it contain both chromium as well as nickel. This you should keep it in mind. This is a type of, you can say, super alloy. So, you see here generally this chromium which increases the resistance of oxidation as well as corrosion, whereas nickel which is added into the austenitic creep resistant steel in order to stabilize the what? Austenitic structure. Once this austenitic structure stabilize, then what happens? You can say its creep resistance property increases. This you should keep it in mind. So, that is why here I have written which generally stabilize the austenitic structure in the presence of large amount of chromium. So, this steel may be used at a operating temperature varying from 650 to 700 degree centigrade temperature. That means, this austenitic creep resistant steel also can have a range of temperature that is 650 to 700 degree centigrade temperature. At that temperature level also it resists the creep, that you should keep it in mind. So, you see some example of this austenitic creep resistant steel is nickel based superalloy like Inconel 617, Inconel 671, Inconel 740, Hyness 230. So, these are the different example of this creep resistant steel. So, this is generally, these are the materials which we generally use for high temperature application. Now, once we join these types of material, then what is its property, how its property changes, that related things also we need to know. So, now we will discuss about creep resistance weldment. So, the heat which involved in the welding process which strongly influences the what? Microstructure and mechanical properties of creep resistant steel. This you should keep it in mind. Whatever the heat generally we use to join those creep resistant steel which I have already discussed in earlier slide. So, that heat during welding affect the microstructure of that steel, and its mechanical property also changes once we do the welding of that creep resistant steel. So, the influencing region of this generally region of this types of welded joint is, you can say, heat affected zone. So, what is heat affected zone? Heat affected zone, you see, just little bit I am just discussing. Let two workpiece material which is creep resistance steel, once we do the welding, you see, this is called weld zone, weld material zone, weld zone. So, or you can say fusion zone, or you can say fusion zone. What does it means? Fusion zone means here the temperature is above melting point temperature. That means, here is the temperature is equal or above the melting point temperature. This you should keep it in mind. So, from this melting boundary, or you can say fluid, or you can say fusion line boundary to till recrystallization temperature. So, for steel it is varying within a range of around, so for mild steel it is generally 273 degree centigrade, you know these things. Okay. So, from this fusion line or melting point temperature to this recrystallization temperature zone, you can say, is known as heat affected zone. So, in this zone generally most of the microstructural changes is taken place. That is why here I have written for creep resistance generally weldment, the influence region is the heat affected zone region. This is actually heat affected zone region. Why it is called heat affected zone region? Because here generally due to heat, here generally some recrystallization or microstructural changes is taken place. That is why it is called, as it is affected by heat, that is why it is called heat affected zone. Okay. And due to this heat, here generally some changes of microstructure also taken place. So, here generally the resulting microstructure and mechanical properties of the heat affected zone are governed by several generally parameters. What are those parameters? So, in heat affected zone parameter depends on what? First, or how much temperature generally subjected to generally this fusion zone. What I am telling under, so it depends on what is the temperature, how much maximum temperature is there during welding in this weld zone, that it is depends on that, as well as it is also depends on this heat affected zone properties depends on also post weld heat treatment, this post heating, preheating, this temperature details I have already explained in earlier lecture, you know these things. So, the resulting microstructure and mechanical property depends on this maximum temperature of this weld zone as well as this post weld heat treatment or preheat temperature, this you should keep it in mind. Here I am just showing a little bit idea what are the things happen in heat affected zone, because this is why it is the main concern zone for creep property as well as you can say critical zone for creep design purpose. This you should know, because the in this heat affected zone generally what happens for low alloy ferritic steel exhibit a gradient in characteristics, in the sense, because in this zone you can find that this heat affected zone there is a different types of range of grain, different type of range of you can say microstructure are there. How it is, that I am going to discuss little bit here. Due to this varying reason, what happens here, most of the changes occur due to creep loading. That is why this is the main concern zone, this you should keep it in mind. That is why here I have shown that in case of low alloy you can say creep resistant steel, they are generally occur this heat affected zone can be divided into mainly 3 different zone. Apart from this 3 different zone, there is another zone is also there, that is called over tempered zone. This over tempered zone is subjected to heat, but it is this over tempered zone generally does not subjected to any what is called recrystallization types of phenomena. This you should keep it in mind. Whereas, the rest of the 3 zone, that this first zone which is you can see this is from this curve itself you can see I have shown that means that melting point zone to around 1100 degree centigrade zone, this zone is called you can say coarse grain heat affect, CG means coarse grain and heat HAZ is heat affected zone. So, here you see this grain size how it look like in this figure I have shown, its grain size is coarse in nature. Just after this region there is a gradient of grain size is taken place, you see after that region where generally called fine grain, FG means fine grain heat affected zone. This grain zone generally varying from 1100 approximately 1100 degree centigrade to AC3 temperature. In case of mild steel or ferritic steel it is around 900 degree or 910 degree centigrade temperature. What I am telling, understand? So, within this zone you see there is a very fine microstructure is taken place. That is why I have written here this zone is generally a gradient zone, means you see somewhere very fine grain, somewhere very coarse grain types of things, its gradient is there, it is not uniform. So, after that you see another zone is there, that is called you can say intercritical, IC means intercritical heat affected zone. This zone is varying from AC3 to AC1, that means critical line AC1 means critical line 1. Okay. So, here its temperature for mild steel within a range of around 723 degree centigrade, you know this thing in case of mild steel, that is why I am written like this. So, around 910 to 723 degree centigrade during this zone, here the grain is further you see increase. So, some gradient is taken place. So, after that zone, so this is the main 3 zone you can say, the one is coarse grain heat affected zone, fine grain heat affected zone and intercritical heat affected zone. Due to this 3 zone you see and its gradient in nature, most of the you see creep related effect is taken place in this zone. This is the most critical zone for creep property or creep design purpose, this you can say. So, apart from this there is another zone is there which is called over tempered zone. This over tempered zone is varying from approximately 700 degree centigrade temperature to AC1 line. Okay. So, you see in this zone what happens, it is undergoes some tempered or tempering types of effect. Due to this tempering types of effect, what happens here generally it result in precipitation coarsening. What I am telling, understand. So, here occurs some precipitation coarsening. I have already explained precipitation coarsening related things in earlier lecture, you know these things. This is the over tempered zone. So, after that this is generally called base material zone. These all are base material zone. Okay. So, in this over tempered zone you can see, in this over tempered zone here generally you can say precipitation coarsening, that means here the grain size further increases. What I am telling, understand. After that generally your base material grain structure is coming. So, you see in this heat affected zone you can say, in this heat affected zone your most of the you see grain structure variation is taken place. Due to this grain structure variation you can say most of the you can say creep related effect is also taken place in this main zone. That is why I have written the influence region for this creep design is heat affected zone. Okay. What happens actually during welding in this creep resistance types of weldment, what happens once we do the welding? Generally the migration of the carbon during welding you can say into the side containing a strong carbide forming element which can produce a decarburized zone in the ferritic steel adjacent to the fusion line. What I am telling, understand, that you see little bit I am drawing this thing, then it will be very clear to you. Let this is our weld zone. Now, what happens in this weld zone, this is called fusion line. Fusion line FL. Fusion line means where the temperature is at the temperature of you can say melting point temperature. So, fusion line, just you see around this fusion line zone, you see around this fusion line zone and it produce a decarburized zone. So, here it produce a decarburized zone. Okay. So, regarding creep rupture property, one thing you should keep it in mind, this carbon depleted zone is weak. So, this whatever the decarburized or carbon depleted zone is there, this zone generally is weak and it is generally surrounded by zone of higher creep strength zone. Okay. So, this zone is surrounded by, you see, just after this zone, rest of the zone you can say rest of the zone is surrounded which has high creep strength. So, strong, here I am writing strong, okay, strong zone, and due to this depleted what is carbon depleted zone which generally become creep related weakest zone, and surrounding zone is generally which has a high or a strong creep property. Due to this thing generally which leads to localized permanent damage you can say in the decarburized heat affected zone which is located in case of low alloy steel part, you can say. What happens actually? This is the main things happen in case of welding due to this recarburization, or you can say carbon depleted zone. You see it's become very weak due to creep property for welding, and what happens due to these things, you can say localized permanent deformation is taken place during creep, you can say creep related effect. That is why here I have written a common preventive method for these types of creep related cracking is done by application of nickel base filler material. This is, you should be, that is why I have written creep resistant steel, I have written austenitic creep resistant steel, there we use chromium and nickel types of composition. Okay. So, what happens if we do generally welding with the help of nickel based filler material, then what happens, it can this nickel based filler material which acts as a preventive medium, you can say, for creep property. That is why I have written a common preventive method for these types of creep related cracking is to use nickel based filler material as a diffusion barrier. What I am telling, understand? Because this nickel based joint generally perform better than those made with austenitic types of filler material. This you should keep it in mind. So, another important point for welding related to creep generally is once we go for doing dissimilar types of weld joint, because dissimilar types of weld joint have a very, you can say, low types of creep property. Why? That I am going to explain, this also you need to know. So, what happens in case of welding, that idea you got related to creep property. So, now you should know also during dissimilar weld joint also what happens. Generally large difference, what happens, large difference and coefficient of thermal expansion of weld as well as parent material, generally large creep strength mismatch and formation of oxide notch at the interface are other promoting parameter in case of creep failure, especially what? Especially for dissimilar metal of welds. In case of dissimilar metal of weld, what happens? We use two different types of material. Let this is one material, this is another material, material type 1, this is material type 2. So, here you see material 1, let us this is mild steel and let us this is aluminum steel. So, you know, say mild steel have a thermal expansion coefficient or thermal conductivity is much lesser than aluminum. So, this dissimilar material property, due to this dissimilar property, you can see there occur a large creep strength mismatch. What I am telling, understand? This large creep strength mismatch also this large property difference which promoting the, which act as a promoting parameter in you can say a creep failure in case of dissimilar types of metal joint. Due to this different properties also, this creep play a critical role in case of dissimilar joint. Now, how we can predict the creep life of a weldment, that related things now I am going to discuss, because we got the idea about what is creep, then what is the creep curve, what is the creep resistance steel, you got the idea in case of weld which zone is more critical zone for creep, then you also got the idea for dissimilar types of joint also creep play a major role, that is why dissimilar joint it is better not to use at high temperature application, what I am telling, understand. So, now we will discuss about how we can predict the what is called creep life of a weldment. So, here we will discuss first what is the creep life of welded zone, what is the creep life of a heat affected zone, and what is the creep life of base material zone. After that, generally I will discuss what is called, what are the different methods generally we use nowadays to predict the creep by using some numerical method. What I am telling, understand, that related concept also I will provide in this lecture. So, well-meant creep life generally can be affected by several different parameters. I have already told you, like due to microstructural changes, due to weld imperfection, it can be due to other factor like weld induced residual stress, then some metallurgical transformation also can affect the what it is called creep life. Apart from these things, a weldment is a multi-material system, you know, because why weldment is a multi-material system? Because once we do the welding, you see in case of fusion welding, you can observe that there occur 3 different zones. One is called fusion zone, just beside side of this zone, which is where generally recrystallization is taken place, that is called heat affected zone. After that there is generally called base material zone. That is why you see, you can say it is a multi material system. Due to these things, what happen? Under creep loading condition, here this each material, that means fusion zone, heat affected zone and this base material zone creep at different rate. So, this different characteristic of this zone is there, that is why its creep rate also will be different, which generally result in development of a complex multi axial stress states. This you should keep it in mind. Because due to this multi material system of weld, here occur a complex multi axial stress state. This you should keep it in mind. So, here the stress state is also not uniform, here multi axial stress state is taken place. That is why in welding creep is a very critical phenomena. So, in general, one thing here you should keep it in mind, weldment creep rupture strength is generally lower than parent material. Here I have shown, you see, here I have shown on example, like you see this solid line represent the base material or parent material and this dotted line represent generally X weld sample. So, for a 600 degree centigrade temperature, you see, for a 600 degree centigrade temperature you can see this is generally represent our stress value and this is generally represent our, okay. This parent material, how this stress varying with time, you see, whereas how the stress varying with time in case of you can say weld material, that you can observe. So, you can say at 600 degree centigrade this parent material has higher creep resistance property than you can say at 650 degree centigrade temperature. And another things also you can observe from this figure, this parent material has you can say higher creep property than you see this is generally weld material property at 600 degree centigrade, it is higher than the 650 degree centigrade temperature. This you should keep it in mind. So, weld generally has you see or weld zone has lesser creep property or lesser creep resistance than parent material. From this figure you can observe. Okay. Now, here generally for a weld joint you see is, that means, and every zone have you can say different creep property, like weld zone have one types of creep strength, then heat affected zone have has another types of creep strength. So, what we observe like weld zone or you can say fusion zone have a creep strength greater than you can say creep strength, fusion zone have a creep strength which is lesser than you can say base material, correct. So, similarly you see heat affected zone have a creep property which is lesser than the base material, have a creep property which is lesser than this base material. So, what should we consider the creep life of a weld specimen? So, among these so that is why what we need to do, we need to find out the creep property for these 3 different zone. Among these 3 zone, whichever you can say has the minimum creep resistance or creep life, that property is considered the creep life of that welded specimen, or you can say weldment specimen. So, that is why here I have written generally design code therefore recommend that is why the design code therefore recommend to consider a weld strength factor in design of component with weldments. Okay. This WSF is generally called weld strength factor. The weld strength factor is defined as the ratio of creep rupture strength of weldment to creep rupture strength of parent material. What I am telling, understand? That means creep rupture strength of weldment divided by creep rupture strength of parent material. Okay. This ratio is called, you can say, weld strength factor. So, generally for designing this weld specimen for creep, generally we need to consider a factor and that factor have a limit. So, that limit generally based on different types of society, or you can say different society provide different types of this WSP limit or WSP values for designing of a weld specimen which is subjected to creep. Like design code who usually consider a constant WSP factor, for example, WSP equal to 0.8, which is given by generally German AD 2000 Markblatt B0. This code generally provide that WSP for a constant you can say material, constant time or constant temperature, this WSP value should be equal to 0.8. This is a constant value. Whereas, some European standard is there for designing this creep related creep design for weld specimen. Generally European Creep Collaborative Committee, that is called ECCC, which design this weld strength factor as, which is not a constant factor, which is a time and temperature dependent factor. This you should keep it in mind, which is also the ratio of creep rupture strength at a particular time t and particular temperature t divided by creep rupture stress or strength of the parent material at a particular time t and this particular temperature t, this ratio. So, which is generally is depends on both time and temperature. So, European Creep Collaborative Committee define weld strength factor for creep design purpose is this you should keep it in mind. So, there is a standard table for particular types of material weld specimen or weldment, this ratio. So, we need to follow those ratio value for designing of what is called creep of a weldment. This you should keep it in mind. Now, here just I am showing the creep behavior characteristics of heat affected zone, then weldment and you can say and base material, from here you can see. So, base material is represented as solid line, then heat affected zone is represented as you see this dotted line and weldment zone have represented in another dotted line. This is a coarse dot and this heat affected zone is fine dotted line. From this figure you can observe that base material zone creep property is higher than this you see weld zone property. So, that is why this is plotted in case of log curve, this you should keep it in mind. So, from here what we can define that what is the creep property of a weldment. So, that is why here I have written, although I have already told you this among these 3 zones creep property which has the minimum creep strength, that minimum one is generally considered the creep strength of that weldment. This you should keep. That is why here I have written the overall creep lifetime of a weldment may be simply defined as minimum creep lifetime of the individual section, that is weld, heat affected zone or parent metal under the homogeneous reference stress determined for the component. That means, for a particular homogeneous reference stage, we need to, you can say, experiment, or we need to analyze the creep strength for these 3 different section like base material, weld zone and heat affected zone. From these 3 zone, whichever has the minimum creep life, that life generally is considered as what creep resistance or creep lifetime of that weldment. This you should keep it in mind. Just here I am defining what is this reference stage we need to consider for creep lifetime prediction. This is actually, this reference stage is equal to P by PL into sigma y. Here this sigma y is yield stress, I have already written, sigma y is yield stress of the material, P is the magnitude of the applied load, whatever the load we are applying for creep test, and PL is the collapse load. That means, what is the load? The load PL means the load at which the rupture or collapse of that specimen is taken place, that is called PL load. Okay. So, the ratio of P by PL into sigma y is known as reference stress. This reference stress generally we use to predict the creep life of weldment. This reference stress we use for heat affected zone, then for parent material zone, and for what it is called base material zone. Generally this reference stress we use. After that, generally what happens, we find out the creep life. Among this, whichever will give us the minimum creep life, that life is considered as the, you see, creep life of that weldment. This you should keep it in mind. Here I am just discussing about how to predict the creep life of a weldment. There are generally 2-3 different types of numerical methods are there, which generally we use to predict the creep life numerically. By using computational method also you can predict the creep life. One of the approach is called generally a reference stress approach. By this reference stress approach we can find the creep life. Here this approach is generally in certain condition can provide accurate prediction for the creep deformation as well as rupture behavior of the component under creep loading condition. This approach, reference stress approach, because of its simplicity or because of its simplified nature, this technique is widely used for analysis and design of engineering component. This you should keep it in mind. But this creep life prediction approach, that is reference stress approach, have a problem, because despite its simplicity of this approach, the basic problem of this approach is it does not account for the stress redistribution which is occurring within the weldment. This you should keep it in mind. So, this stress redistribution which is occur due to different creep deformation behavior of the weldment constituents, because during welding if we use this reference approach, generally in reference approach this is the basic problem. Here we do not consider this stress redistribution which generally occur in a weldment, because a weldment have different constituents. So, this generally this process generally does not account for the stress redistribution which is occurring in the weldment due to the different creep deformation behavior of the weldment constituent. This you should keep it. This is the basic problem of this reference stress approach. So, this is one approach we can. So, here I am not going in details, further details about this approach, just I am giving you some insight of approach used for weldment creep life prediction. So, this is one approach. Here also you can get quite accurate result. Then what happens, for further accuracy we use some other technique. One of the techniques here I am showing is called finite element analysis techniques. In finite element analysis techniques also there are 2-3 different approach we use. So, first approach is generally called displacement based finite element analysis procedure. It is a implicit techniques. So, here what generally we used to do in this method, generally here we use some commercial FE codes which are available, which are usually able to consider only a few simple creep constitutive model. One of the example of this constitutive model is Norton creep model. Some other creep model also is also there. Some of the model is generally is called RN model. Then what happens, one model is called some other constitutive model like R Singh model. Okay, these are all creep prediction you can or creep constitutive model. So, generally in FE code these types of creep constitutive models are available. By using this thing, generally what we can do, we can predict the creep life of a structure. So, here generally the user, as here some simple constitutive models are there, that is why what happens in FE model, finite element analysis, the user can define his own constitutive model or own, you can say user define user material subroutine to implement more sophisticated creep model with several internal state variable also. What I am telling, understand? Like as per your requirement, you can incorporate or you can write your own user defined your subroutine which can consider damage, then special types of stress and temperature function, etc. So, that also you can incorporate there, and by using FE analysis you can find out what it is called creep life by using displacement based FE procedure. Then what happens, another process also for creep life prediction of elements are there, that is generally called FECDM process. This is called, full form of FECDM is finite element continuum damage mechanics. This is another approach, is generally more accurate, which generally consider continuous stress redistribution and damage formation within whole life of a component. So, this FECDM method is more accurate because it is generally considered, this technique generally consider continuous stress redistribution. Like I have already told you, a reference stress approach does not consider this continuous stress redistribution, but this technique generally consider this continuous stress redistribution and damage formation within the whole life of component. Basically, a successful application of FECDM for analysis of a structure with or without welding, this technique both the case we can use, and which can predict not only the lifetime of the component, this FECDM also can predict the deformation behavior and failure location also. This is very important approach, this you can say. FECDM, that is why widely used in well life creep prediction purpose. So, apart from this FECDM approach, another approach also is there, that is called Likon method. This is also a very popular method, that is the full form of Likon method is called linear interpolation constitutive equation method. This method can be used to predict the creep rupture behavior of weldment very accurate way. What I am telling, understand? This Likon method generally predict long term creep failure behavior of material or weldment using the result from several short term creep crack incubation. This you should keep it in mind. So, this is the main features of this Likon method. Here generally we can predict the long term creep failure behavior. This long term creep failure behavior we are predicting by what? Several short term creep crack incubation test. This you should keep it in mind, or CCI creep crack incubation test result. By using this short term CCI test data, we can predict the long term creep failure behavior. This you should keep it. This, that is why also this technique also have wide application in the field of weldment creep life prediction. So, just here I am giving an example related to this creep property of a welded specimen of grade 91 steel, that is generally in the categories of creep resistance steel. So, here you see this grade 91 steel, you can see how the creep property is varying. This is the experimental property I am showing. Here in this first figure you can see the weldment, how the strain as well as time is varying at a temperature of 550 degree centigrade, creep property is varying. Then you see this weldment as you see less time than heat affected zone as well as this base material zone. So, with time and strain, how the creep curves or how the creep property is varying in weld metal, heat affected and base material for this creep resistant steel grade 91 steel, that I am showing here. This is one of the example which I have taken from this reference. Then this is the generally rupture time versus stress value for base material, weld material and heat affected zone at a temperature of 550 degree centigrade temperature. From here also you can have idea, you see this rupture stress and you see rupture time. This is generally this black dotted line represent this base material. So, base material has rupture time as well as rupture stress value is higher than you see weld zone as well as heat affected zone. And another figure also I am showing that at elevated temperature, that means 550 degree centigrade temperature, how the stress strain curve or engineering stress strain curve of what is called, this is actually your base material or parent material, this is actually your weld material and this is actually your heat affected zone material, how it is varying, that I am showing. So, from this curve, these are all experimental data. From this curve what you can observe, that you see how the creep property varying in a welded specimen. Okay. So, this all about today's lecture. These are the references which I have followed for this lecture. Thank you.